We continue our discussion of molecular orbital theory and polyatomic molecules with a simple review of variation theory as applied to the linear combination of atomic orbitals. You recall that our molecular orbital wave functions are simply a linear combination of atomic orbitals, represented by phi here, and in this case n represents the number of atomic orbitals in our linear combination. The coefficients are the variational parameters in this circumstance, which means what we're going to try to do in our computation is find the coefficient values which lead to the minimum energy and give us a wave function which is closest to the actual wave function of the molecule. Now, the way we do that, of course, is we take the derivative of the energy with respect to each of the coefficients and set that equal to 0 and then solve. And of course, if we've got n atomic orbitals, we're going to have n coefficients, and that means we have n derivatives that we have to take. So to be more specific, suppose we have 4 atomic orbitals in our linear combination, which means we're going to generate 4 molecular orbitals. We're going to have 4 derivatives that we have to take and set equal to 0. And that means we're going to have to solve 4 simultaneous equations. So the number of simultaneous equations is equal to the number of atomic orbitals in our linear combination. And to solve those, we're going to use a secular determinant, which is going to have the same number of rows and columns as the number of atomic orbitals. So if we have n atomic orbitals, we'll have an n by n determinant. If we have 4 atomic orbitals, we'll have a 4 by 4 determinant with 4 rows and 4 columns. So let's look at a specific example. Here's a determinant that would correspond to a linear combination of 4 atomic orbitals where we have 4 rows and 4 columns. The subscript on the elements within the matrix correspond to the rows in the column. So H11 corresponds to row 1, column 1, for example, and S32 down here corresponds to row 3, column 2. If you take a close look at the 4 by 4 determinant, you'll see that each of these subscripts do indeed represent the row and column number corresponding to the position of that particular element. We set the determinant equal to 0 and we solve using basic rules of determinants. Now, let's define each of the elements in this particular determinant. They're often referred to as matrix elements. And in this case, we'll start with the diagonal elements, labeled HAA. AA means row and column are the same, so that's all of these elements here along the diagonal of our determinant. And in this case, we'll notice that the integral involves our 2 functions, atomic orbital functions, which are the same, and the operated on by the Hamiltonian operator for the molecule. So these are all along the diagonal referred to as HAA. The HAB is referred to as our resonance integral, and our resonance integral corresponds to 2 different atomic orbitals in this integral, and these are going to be all the off-diagonal elements that are represented in this particular determinant. The S symbols refer to something as the overlap integral, and they simply are integrals involving the product of 2 atomic orbitals. SAA means the atomic orbitals are the same, and of course we'll recognize this situation if we have the product of 2 atomic orbitals integrating over all space. If those orbitals are normalized, then that's going to be equal to 1. And these, of course, are going to fall on the diagonal of our determinant. The SAB corresponds to a situation where the atomic orbitals are different in that integral, and that will find in this overlap integral between 2 different atomic orbitals, the values generally range between 0 and 1, 0 corresponding no overlap whatsoever, 1 corresponding to total overlap, and that only occurs when those orbitals are in fact the same. These are going to fall off diagonal in our particular determinant. Now, of course, what we'll note is that we have a 4 by 4 determinant, and that will yield 4 energies corresponding to 4 molecular orbitals. Now we look at the application of this variation theory to something called Huckel molecular orbital theory. This is a theory that's applied to pi electron systems and assumes a rigid sigma bond framework, meaning that sigma bonds don't enter into the computation at all. We're applying this only to the pi electron structure of our molecule. In this case, our pi orbitals are generated by taking linear combinations of the atomic 2p orbitals that are part of the pi framework. Again, we'll set up a secular determinant. The dimensionality determinant depends on the number of p orbitals involved in the pi framework. And we're going to actually define a Greek character alpha as being equal to HAA, where remember HAA correspond to all the diagonal elements in our determinant, and beta is going to correspond to the off-diagonal elements in our determinant. Now, there are some assumptions that are going to go into this Huckel molecular orbital theory. One is that the beta, HAB, is going to be equal to 0 unless the carbons are next to each other in the structure of the molecule. The other is associated with the overlap integral SAB, and in this case, of course, we note that when the two atomic orbitals are the same due to normalization factors that we talked about on the previous slide, this is going to be equal to 1. But the assumption here, or the approximation that we're going to use here, is that if the atomic orbitals are different, then the overlap integral is going to be equal to 0. Even if the two atoms are next to each other, we're saying those two p orbitals do not overlap, that the overlap is equal to 0. This is a pretty significant approximation and does lead to error. We'll talk about that a little bit later. All right, let's apply HMO theory to a simple molecule, the simplest possible molecule with the carbon-carbon double bond with the pi framework, and that would be ethene, of course. In this situation, we'll note that, of course, the pi framework is due to the overlap of p orbitals perpendicular to the plane of the molecule. And so because we have 2 carbon atoms in our molecule and 2 p orbitals, we're going to have a 2 by 2 determinant. And using the designations we defined earlier, the diagonal H11 is going to correspond to alpha, as is H22. Since carbon atoms 1 and 2 are adjacent to each other, they're equal to beta, H12 and H21. And of course the overlap integrals, S11 is going to be equal to 1, and so we have alpha minus E times S11, so that just becomes alpha minus E. And the off diagonal, S12, is of course equal to 0, as we noted in our approximation. So the second term in the integral, beta minus E times S, becomes beta minus 0, so we'll notice the off diagonal elements are both 0. Now, if you remember basic determinant theory and how these things work, we multiply alpha minus E times alpha minus E and subtract from that beta times beta. We can use MathCAD to expand these determinants, and there is a video that you should watch which shows you how to use MathCAD to generate determinants and go through the expansion. When we do that, we're going to end up with, as noted here, alpha minus E squared minus beta squared being equal to 0, which we then solve for E, the energy, and when we solve for energy we notice that we get alpha, energy is equal to alpha plus or minus beta. Now we have obviously 2 energy terms here. We have energy is equal to alpha minus beta, and energy is equal to alpha plus beta. These are the 2 energy levels corresponding to the 2 molecular orbitals. Now remember, of course, we had 2 atomic orbitals, so we get 2 molecular orbitals, and their energies are alpha plus beta and alpha minus beta. It is important to note that beta is less than 0, and so therefore the lowest energy term is going to be alpha plus beta. Here we have the energy level diagram showing the two pi orbitals in the case of ethene, alpha plus beta again being the lowest energy, alpha minus beta being the higher energy. Alpha here represents the energy of the atomic orbitals by themselves. So alpha plus beta is a bonding orbital, and alpha minus beta is an anti-bonding orbital because its energy is higher than the energy of the atomic orbitals. We have two electrons in the system, one electron coming from each of the carbon atoms, and so to determine the electron configuration, we just put those two electrons in the lowest energy orbital, alpha plus beta. The total energy, therefore, is just equal to 2 times alpha plus beta again being the energy of the molecular orbital here. Right, so we have a simple example of ethene where we show there are two electrons in a lower energy orbital, the energy corresponding to alpha plus beta. The total electronic energy is 2 alpha plus 2 beta. It's important to remember this because in our next video we'll be talking about Huckel molecular orbital theory as it applies to butadiene, and we will compare the energy that we get from that to that of the ethene molecule.